This is part 3 of my introductory series to eigenvalues and eigenvectors. I'm following the material in the book, but just trying to illustrate it in more detail. And so in the last one, we showed how to find eigenvalues, and I'm using this specific matrix, and I want to continue using it the same one I used in part 2 and part 1 is 4, 3, minus 1, 0. In the last part, we showed that lambda is equal to 3 and lambda is equal to 1 are eigenvalues for this matrix. Now the question is, how do we find the eigenvector that goes with these eigenvalues? Okay, so we're going to start with lambda equal to 3, and we build what we know to be true, that if you're going to be an eigenvector, then A times an eigenvector would end up being 3 times that eigenvector after it has been multiplied by A. And so let's do that. Minus 1, 3. I'm sorry, it's minus 1. It's a 4. 3 minus 1, 0. X times y is going to be just 3 times x times y. Writing this as a system of equations, I have 4x plus 3y, 4x plus 3y is equal to 3x, and I have minus x plus 0y is equal to 3y. Rewriting this system as follows, I'll bring the 3x to the other side, and I have x plus 3y equals 0, and I have a minus x minus x minus 3y is equal to 0. Both of these equations imply that that x is always equal to minus 3y. And this is our condition on our eigenvector. So any vector v that satisfies this condition, that that the x value is just minus 3 times the y value, will be an eigenvector. So if y is 1, so that implies, if y is a 1, that implies this is an eigenvector. If y is 2, I would get minus 6, 2. If y is a minus 2, I would get 6, negative 2. And so for each eigenvalue, so for the eigenvalue of 3, I have multiple vectors I can call eigenvectors. Each one of these, when multiplied by A, are stretched by the amount of 3. In general, we always choose the simplest one, the smallest one, and so we could choose minus 3, 1 or 3, negative 1. And so that's how we find an eigenvalue, an eigenvector. Let's do it again with lambda is equal to 1. That's our second eigenvalue. So I'll go to the next slide and do it one more time. Okay, so again, our matrix is 4, 3, minus 1, 0, and we have an eigenvalue that we found from the characteristic equation of is 1. The other one was lambda is equal to 3. We solve for the eigenvector. Solve for eigenvector by rebuilding the equation that 4, 3, minus 1, 0 times xy is going to equal to 1, that's the eigenvalue, times xy. Writing this as a system, I have 4x plus 3y is equal to x, and I have minus x plus 0y is equal to y. And taking this and bringing the x and y to the other side, I have that 3x plus 3y is equal to 0. And I have a negative x minus y. Negative x minus y is equal to 0. And again, both of these equations imply that, in this case I can say y is equal to negative x. And so my eigenvector has to be something of the form where the y value is the negative of the x value. So anything like this will work. Let me just make that prettier. So I'm taking this condition that y has to be minus x and building a vector that satisfies that. And so many possible eigenvectors, of course, infinite number of them, but 1 minus 1, or if x is a negative 1, I would have negative 1, 1. If x is a 2, I would have 2, negative 2, and so on. In general, it's always best to use the simplest one, and so I would probably opt for this very first one. But they're all perfectly good, and as we move on and use these things to solve differential equations, we can choose any eigenvector we want, but always in our best interest to keep it simple. Okay, that's the end of part 3.